All right, looking at question 9 in your notes, it says this illustration is showing a dilation with a scale factor of -2. Now, when it's asking for the ratio, remember that these are links. When we put 2 points names beside each other without a segment bar or a symbol of any kind, it's talking about a distance. So we're talking about the distance from R prime to J in comparison to the distance from the original point R to J. Now, can a distance be negative? No, it cannot. So be careful thinking that your scale factor and your ratios are always the same exact number. If your scale factor can be negative, but your ratios of sides or distances cannot be negative because distances and side lengths can't be negative. So this is a positive distance. This is a positive distance. So when you compare them, you're going to get a positive number. So even though the scale factor is -2, the ratio of the side lengths is a +2. Okay, so it is impossible to end up with a negative value when you're talking about the ratio of two corresponding sides or distances. All right, so your scale factor is negative, but that doesn't mean those ratios are negative. Let's look at our next animation. All this wants us to do is to look at the qualities and the properties that we looked at with the first animation and see if they still apply when we distort or change these triangles. So this was our original triangle STR and our image triangle, and we looked at the ratio of the sides and the angle measures with that. If I change this triangle in any way, we're distorting it, did those properties change? I hope you saw they did not. We're looking at the ratio of the sides. It's still the same as my scale factor. The corresponding angles, even though the degrees changed, the comparison of the angles did not. Angle SRT is still congruent to angle S prime, R prime, T prime. So the properties are not changing. Still, when I go to a scale factor of 1, I could create a congruent figure. When I go to a scale factor between 0 and 1, I'm reducing the figure size and getting closer to point J. When it's greater than 1, it's an enlargement and getting farther away from J. When I go to a scale factor of 0, it still goes to a point, a single point, which is the center of dilation. When I go to a negative scale factor, I'm still creating a reduction between 0 and -1 and a 180-degree rotation around point J. A scale factor of -1, they're congruent triangles, but again, we still have a rotation of 180 degrees. Notice your ratio of the sides is positive, even though your scale factor is negative. And if I go between or a smaller number than -1 for my scale factor, I'm increasing or enlarging the figure. It's getting farther away from J, but again, those ratio of the sides is a positive number. So all of the observations we noticed before still hold true. So there wasn't anything magic about our original triangle RST. It would work for any triangle, those properties. So question 10, do the relationships you found in question 8 hold true even if the triangle is distorted? Your answer is yes. Those properties still hold true. So throughout our exploration, we have seen that dilations create triangles that have congruent corresponding angles and proportional corresponding sides. And so we have a definition that we can apply to similar polygons using these properties. So it states, and this is number 11 in your notes, that two polygons are similar if and only if all of the pairs of corresponding angles are congruent and all of the pairs of corresponding sides are proportional. Remember, if you see this phrase, if and only if, that is called a biconditional statement, meaning we can read it the way it is written, and it's true, and we can look at its converse, which remember means switching the hypothesis and conclusion, and it's still a true statement. So that means if all the pairs of corresponding angles are congruent and all the pairs of corresponding sides are proportional, then that would declare that the two polygons are similar. So looking at question number 12, we can use this definition to determine which of these figures are similar and which ones are not similar. So we're looking to see if all the corresponding angles are congruent and all the corresponding sides are proportional. If they are, then those figures are similar. So looking at these two triangles, I can see that this angle is congruent to that one because they both have 3 arcs in them. This one is congruent to that one, they both have 1 arc. And this one is congruent to that one, they both have 2 arcs. When I look at the ratio of the 2 sides, the corresponding sides, I always go ahead and put my image over my pre-image because I know that that would give me the scale factor as well. So I assume the first figure given is the original or the pre-image, and the second one would be the image. So when I'm comparing the sides, I would compare the longest side of this triangle to the longest side of that triangle. So I would put 6 over 3, which is 2. And then the medium sides would be the 2 and the 1. 2 over 1 is also 2. And, I'm sorry, that's the smallest side. The medium sides would be 4 and 2. 4 over 2 is also 2. So since 6 over 3 is 2, 2 over 1 is 2, and 4 over 2 is 2, all of the sides are proportional. So under similar, you're going to put A. Those two figures are similar. When I look at the pair B here, I see that all 4 angles of this figure are 90 degrees, and all 4 angles of this figure are 90 degrees, so it does meet that criteria that the corresponding angles are congruent. But when I start to look at the corresponding sides, I have some of them where the pairs are congruent, and some of them where the pairs are not congruent. So the ones that have congruent sides would have a ratio of 1, but the ones that don't have congruent sides would not have a ratio of 1. So therefore the corresponding sides are not proportional because all of those ratios would have to be the same. So we would put B under the column for not similar because the corresponding sides are not proportional. Now hopefully you would know just by looking at C that these cannot be similar because they're not even the same shape. This has 4 sides, so it's a quadrilateral. This one has 5, it's a pentagon. And we can see that all 4 of these angles are 90 degrees and all 5 of these angles are not 90 degrees. So definitely C would go under not similar. We can only compare triangles to triangles, pentagons to pentagons. We cannot compare a quadrilateral to a pentagon. So finally in option D, we have all 4 angles of both figures being 90 degrees, so the corresponding angles are congruent. And all the sides of this figure are congruent to each other, and all the sides of this figure are congruent to each other. So no matter what those numbers are, the ratios would all be the same. So for instance, if all of these sides are 2 and all of these sides are 7, then every single ratio would be 7 over 2, 7 over 2, 7 over 2, 7 over 2. So they are all proportional. So figure D would go under similar. So our final wrap-up question says, how could we use a dilation to construct an image that is equal in size to a pre-image, so they're congruent, but is rotated 180 degrees about a point? So remember, to get the 180 degree rotation, we have to have what kind of scale factor? It has to be negative, right? But for them to be congruent, the dilation scale factor has to either be 1 or -1. So in this case, we would need to use a scale factor of -1. It would still be equal in size to the pre-image, but it would be rotated 180 degrees around that point of dilation. On your homework tonight, I did want to help you get started with one of the problems that seems to be a challenge for most students. And so if you'll look at number 12 on your homework with me, I'll help you get started on that. It says, suppose a triangle was dilated by a scale factor of S with a center of dilation point P, and the image of that dilation was dilated by a scale factor of T with a center of dilation still at point P. What single transformation would have the same effect on the original triangle? So remember, single means 1, and we are going to justify our answer with an image. So I would suggest that you start off just drawing a random triangle and giving it some side lengths. Okay, so if I said this side is 1, this side is 3, this side is 4. And I'm going to have a point, random point P here. Well, I'm going to dilate this figure with some scale factor that I can make up. So for instance, I can say I want S to be 2. Well, then I'm going to create a triangle that's similar to this one, twice as far from P. All of these side lengths will double, and I would create that triangle. And then I would do another dilation to that new triangle with a new scale factor. So this time I might say, well, I'm going to let this scale factor be 3. So I would take this triangle, make it 3 times as far from P, and all of the side lengths would triple in length. And then I would think about, well, how could I get from here to here in one step? So even though these are generic values, you can assign numbers to them. I would make sure you would do different numbers here, so I wouldn't make both of them 2 or both of them 3. I would make them different so that you can clearly see what would get you from your first figure to your final one in one step. So hopefully that'll get you started on that. Again, the drawing is key to help you answer that. All right, good luck.